I'm Frank Mateo. I'm hardware.
Hi, I'm Eliana Montalegre, and I'll be doing software and hardware components.
Hello, my name is Miguelina Espinal, and I will also be working on the software side.
So as of 2006, only 40% of the blood collected each year is donated in developing countries, which are home to 80% of the world's total population. An overwhelming 99% of the 500,000 women who die each year during pregnancy and childbirth live in these developing countries. They die because of hemorrhages, which invariably requires blood transfusion, the most common cause of maternal deaths. However, in Africa specifically, approximately 70% of the blood transfusions are given to children with severe anemia due to the malaria, the leading cause of death among children under the age of 5 there. Because of the lack of supply or the lack of accessibility in order to receive the blood in time, more people are dying than they have to. These deaths could easily be prevented. Next slide.
This is our need. There's a need for medical supplies in underdeveloped countries. There is currently a void in the use of drones for medical, but currently nonprofit organizations are testing them in the remote areas of the world. Next slide. The picture you guys are seeing is currently what was a test that UNICEF did in a rural area of Africa. They wanted to see if they could use a drone to supply medical supplies. Next slide.
Our market and competition. On the left, you can see a zipline plane, and on the right is a Skyports drone. Both I will explain in the next slide. The drone delivery market is expected to rise in demand in the next decade. During COVID-19, the need for medical supplies has increased, and now more than ever, people don't feel as safe when a person delivers a package to their door. Places that are hit hard with natural disasters are hard to reach, and they need more medical supplies, especially during an event like that. And all these issues can be resolved with drone delivery. Companies like Zipline, which was founded in 2014, Skyports, which is founded in 2018, and Matternet, which is founded in 2018, are all delivering medical supplies. Zipline has operations in Rwanda, delivering blood and plasma to hard-to-reach areas. They use the same plane launching technology that is used on U.S. carriers, which allow for a faster takeoff and less drag because there is no landing gear on the plane. Skyports is a company based in Asia. An advantage of this company is its ability to carry a big payload capacity, allowing them to deliver all types of supplies, not just medical supplies. And Matternet is a startup that can deliver medical supplies similar to Zipline. However, Matternet is a quadcopter, not a plane, so it has vertical takeoff and landing, which it allows it to get to better areas. And they also just expanded to Tokyo, Japan, with Japan Airlines as well. Medical supply delivery is not the only drone delivery market high in demand, though. Companies like Amazon, FedEx, Walmart are all looking to cut delivery times in half for their products. So they're pushing most of their profits into drone technology, which could make more profits for them in the future.
So here we have, we're ranking our needs using the analytical hierarchy process. We decided on a list of factors of which were most important to us in our project and design, and implemented a pairwise comparison matrix in order to weigh each factor and compare them to each other. As you can see, the price and cost and its durability is one of the more important factors that we were looking into in our project. Next slide.
So our project will create an autonomous RC plane that will deliver medical supplies to communities and hospitals in need. The plane will use an autonomous software system that will guide it to its destination without the need for the user to pilot it, thus allowing anyone to be able to use the drone. To beat the competition in the market, our plane will have an increased weight capacity to be able to carry more supplies. The use of drones is becoming more frequent worldwide, especially in recent years to fill different roles to improve the lives of people by gathering data, collect materials, and aid people in defense. Our project will be a big benefit to small countries and communities which are hard to reach by land. Next slide.
So when delving into such a project, you must come up with specific requirements you want to meet in order to ensure the project's success. In order to fulfill the requirement specification, one must satisfy both the engineering requirements and the marketing requirements. So For our project, we want it to be affordable, energy efficient, able to carry a sustainable amount of weight, and have a fast delivery time and durable design. On the right, you can see our marketing and engineering matrix. And in our project, we decided that battery life and speed are extremely important for us so we can go to these hard to reach places. And also that the cost and the weight is important for us too, because we want to be able to carry a substantial amount of weight so that we can do these deliveries. Next slide.
This is our project requirement, our objective tree. So the purpose of a remote autonomous RC plane is to transport a small payload to an area of need among the medical community in either a hospital or rural area. The most important is that it can be packable, meaning it can carry and easily transport anywhere in the world due to its small size. And the software capability will allow for the drone to fly to and from the assigned location while being tracked by the user. Next slide.
So here's a basic description of our system and how it's going to work. We have the user's input, which would be like the medical professional on the application that we can show you later on. And then it will be put into the system. So there can be a loading dock, and then the people will put it in to the plane, like whatever they have to package and deliver. So that's going to communicate with the autonomous flight software, whatever the user input put in. It's going to put the coordinates wherever it's going to go. So that's going to communicate with the flight controller. The flight controller is going to then fly to the places that it needs to go at a certain altitude. The sensors are going to be involved with trying to avoid obstacles, calculating the wind, and that's going to be in relation with the electronic speed controller in the motors in order for it to fully work. Next slide. So we have key design modules and descriptions and specifications. It incorporates things such as our function decomposition, hardware design, software design in both of its implementations and demonstrations, performing iterations to develop the optimal design in both our hardware and software design. Next slide.
This is our functional decomposition level 0. As you can see the picture to the right, it shows how the user input and the DC power and software go to the RC plane and microcontroller, and then the drone's able to take off and drop off a medical package. Sensors, which puts the GPS input onto the drone so it can avoid obstacles. This next slide is the functional decomposition level 1. It's the module, which is the flight controller, the input, which is the data and power, the output, which is the power, which is servo motors. Next slide is the functional decomposition level 1. And it is the picture on the right shows autonomous flight software, how it sends the voltage signals to the flight controller, and how it's powered by the rechargeable battery. Next slide.
This is hardware design and project selection. So I was going to plan on making my own plane and designing my own plane. However, it became a challenge as I'm not a mechanical engineer. So I decided to take someone else's idea, and this the person who designed it his name is Spike Webb. He designed this plane called Gemini version 2, and it's a long duration plane, and then it can also carry a payload. Its wingspan is 10 feet 6 inches wide. The cruise speed is about 25 to 30 miles per hour. The weight of the plane is about 15 pounds and 5 pounds extra for the payload. And then the average flight time is about 2 hours, 1 hour to the destination and 1 hour back. The ceiling height of this plane is 13,000 feet. However, due to FAA regulations, a UAV can only operate about 400 feet. And this is the schematic for the electronics for the plane. As you can see, we're going to be using a LiPo battery pack, and it's being connected to the two ESCs, and the two ESCs are being connected to a motor. I had to switch the wires for the motor 2 because I needed the motor to spin in the opposite direction as motor 1, because I don't know if you know it or not, but for a single engine plane, the plane tends to roll in the direction that the propeller is spinning. So for a dual engine plane, that is canceled out when both motors are spinning in the opposite direction. And each ESC has a base eliminator circuit, base limiter current, circuit. It has a 5.5 volts lead coming out of each one, and I only needed one to power the temporary receiver. So I had to remove the red lead from the ESC number 2, and then that allowed me to power the receiver. And then we have the five servo motors, the ailerons which control roll, and horizontal stabilizers which control pitch, and then the rudder. And then you can see on the right is our Tesla style LiPo battery pack. And as I said before, we're going to use a battery pack. I'm going to build my battery pack because because a couple LiPo batteries won't do it. We need enough battery power to get it to its destination and back. So it has a voltage rating of about 11.1 volts, and then the total capacity is about 42,000 milliamps. And then this is the schematic for the spec sheet for the motor, and then there's the spec sheet for the ESC. As you can see, there's a continuous output of 60 amps, and the motor is asking for 50 amps. I did this on purpose so that it would be getting enough amounts of amps at all times, so that I can have it at full throttle. And then on the next page, as you can see, this is our flight controller. It's the Pixhawk 4. It is one of the best in the business. It has great sensors on it, so it can let us know what heights and what speed it's at. And then here is the demonstration video. I'm going to be powering up the motors. As you can see, they're spinning, and they're spinning in the right direction. And then that's the rudder being used. And then next, I'm going to be using the horizontal stabilizers, and then the ailerons. And next slide.
So this is our firmware design. We've been working with both DroneKit Python and ArduPilot. Both of these help us communicate directly with our plane using Mavlink. They allow advanced data logging, analysis, and simulation tools so that we can test our autopilot system. On our left, we have one of the algorithms that we're using. We have a function in that accepts the target altitude in centimeters as an argument, and then it slowly increases the output of our RC channel, which in this instance would be 3. Which is the throttle channel, while continuously monitoring the plane's altitude. Once the altitude is reached, the function then returns. And on our right, we have our second algorithm, which is holding the target altitude. So we want to continuously monitor the plane's altitude and apply slight adjustments to the throttle accordingly. This function is invoked after reaching the target altitude and is executed in a separate thread so that it's always attempting to hold the target altitude during the whole entire flight. Next slide.
So this is a demonstration of how the software will control the RC plane. So when the plane is given a mission, the waypoints will be set for the plane to follow. So I set 3 points there, 3 destinations for the plane to go to. Then once the plane is switching to auto mode, it will automatically go to each waypoint in the order that it was given. Then once the RTL command is given, it will tell the plane to head back home and start the landing sequence once it reaches space. Then the plane will start descending altitude, and once the altitude reaches 0, the plane will disarm itself. So the software keeps an update on which height the plane is and when it starts descending and when it starts hitting the ground. When the plane is disarmed, it will essentially be shutting itself off.
So in order to do this, we obviously have to have some sort of math to prove it. So in our related theory, in order to know which direction to turn, we use the absolute angle of the current direction and the destination, which is needed for this. We want to get the absolute angle of the current direction it's in, the absolute angle of the way it needs to go, and then the difference between them both. To get the absolute angle, the relative angle should be calculated, and then the absolute angle can be derived from it from forming a triangle and using Pythagorean's theorem. For example, we can see that theta is the relative angle of the direction from point 1 to point 2 in our first chart on the left. Then we can change the relative angle to the absolute angle with the following guidelines using the quadrant on our picture on the right. Then we can compare results to the guidelines and decide whether the plane will turn left or right when alpha minus beta is the absolute value of the difference between the angle of the current direction and the destination. So if it falls between the guidelines, let's say in the first one, it's going to turn left, and on the bottom guidelines, it would turn right. Next slide. So before Finton plays the video, I'm going to just describe this. So this is an example of a simulation of what the app would look like for the user side, the user interface. So for example, the medical professional would go into this app, log in through their hospital. I just put Montefiore Hospital because that's where my sister works. So that's the first one I thought of. So this would be the welcome page for when they log in, make sure the GPS is on so it knows where to go. So this is like they can start their order, their home screen. It shows you if you have any current orders, the estimated time of arrival, how many orders you've done in the past. So you can click on start order, and then it'll bring you to like a list of items. So for example, I added gloves to my cart, and then I increased it to 2 gloves. It's just a quick checkout. If you want, you can slide the quick checkout just a further up so you can have more of a good view. We would have the face mask. I just added that. And you can see that the delivery time can be altered. So it could be ASAP, as soon as possible, or it can be for a later time, like 9 o'clock at night. So here we placed our order, and it tells us the estimated time, which would be 3:26. It gave us a preview of where it was. So it was a packaging the order. And if you want, you can click on the screen where it shows the map, and it kind of gives you an idea of where the plane is currently at, because medical professionals, obviously things can change with someone's health in a second. So just to kind of have an idea of where the plane is at, so you can start, you can plan accordingly to whatever happens in the medical emergencies. Next slide. So here we have our risk analysis and testing. Test cases define exactly what the module must do. Testing prevents future mistakes since the development of the module is complete when the test is passed. So on our left, we have our unit testing. It tests functionality of the system in isolation. So for that, in isolation, we tested and debugged our algorithms and firmware. We tested our separate hardware components. And on the right, we have our integration testing, which helps ensure that requirements are being met while also allowing us to think about extreme cases. So we did firmware being tested at the rate when testing the simulation, and all hardware components are working with the controller as of right now, because later on we will be connecting it together to our software, because our software right now we're using a simulation test to make sure that it's perfected first before we fly our actual plane. This allows us to avoid any possible issues due to crashing our model and having to rebuild it. Next slide.
This is our project schedule. As you can see, we've done some hardware and software work, and now over the winter break, we're going to start building the drone and building the battery pack as well. And then we're going to connect the autopilot flight controller to the motors and to the plane and start testing, and then we'll finish testing the drone, and then also finish making that app hopefully by the end of the next semester.
So this is our go, no-go milestone. We have where we split it into the fall semester, winter break, and spring semester. I'm going to go into a little bit more detail about what we're going to do in the winter break and the spring semester. But so far in our fall semester, we've met most of our hit points that we wanted to hit with researching and unit testing and designing. Next slide. We have our cost analysis. So it's just a supply list, quantity, how much the price was, and the total cost. So we ended up coming up to $299 for what we spend and what we plan to just spend a little bit. So that's around the range. Next slide. So for our future work, the winter break, we want to put the rotors onto the drone body so we can download the software onto it. We want to at least try to meet up as a team in person to conduct a takeoff and landing test flight in an open area. Obviously, it's been kind of hard to do that right now because of COVID and having to meet. So we're going to try to keep social distancing matters while doing this. And we're going to try to make a better battery, which consists of what Finchen talked about before with our Tesla style battery. And in the spring semester, we want to implement machine learning, object detection, and more features into the software. We want to use sensors on our drone, and we're going to have 2 cameras on it. So we can try to avoid any obstacles, such as like a tree or something like that you don't want to fly into. And then we have our firmware functioning with mission planners, what we also plan to do. Next slide.
This is our code standards and restraints. As you can see by the picture, this is one of the most recent law passed by the FAA, which places limitations on unmanned drones. The biggest thing from this is the height of our drone, how much our drone can weigh, and when we can fly our drone, which will be only in the daytime. Next slide.
So this is our ethics issues. So one of the biggest concerns with our project is that it could be hacked by others, and because it is an autonomous drone, having a hack will give total control to the intruder of the drone, and they can change the destination to where the drone is headed. And another one is that because drones are a relatively new technology, not a lot of people are willing to trust machines with important medical supplies in case of the failure of the machine and the supplies being lost. And other people just don't feel comfortable with having drones fly over them all the time. So they may not agree with their hospital using drones for deliveries. Next slide.
This is our reference slide, if you want to take a look at it for a second. And then any questions, any concern, just let us know.
Okay, I have a question, okay?
Okay.
2 questions. You're going to design a drone, okay? You're going to control this drone. It's very important the drone is under a dragging force, and this dragging force creates vibrations. And these vibrations can affect your object recognition and object identification recognition. My question is if you're planning to include some vibration sensor and make a feedback to offset for this problem. This is my question. And this also applies to the first project on the artificial hand from a drone, applies also there. If you're planning to include some vibration sensor feedback system to offset for these involuntary movements.
Yeah, so not only are we planning on the software part, but we're also planning on the hardware part as well. We're going to make sure that there's enough, like a foam on the inside for the electronics and the sensors as well, to make sure that that limits the vibration. But hopefully Eliana can explain the software as well.
More is hardware related.
Like as in we'll put like a foam inside so that it has like a cushion. The electronics have a cushion, so then that way that they don't vibrate as much.
Eliana, the software, Eliana.
So yeah, that's a good point that you pointed out. So like you said, hopefully next semester in the spring semester, we'll be able to include and have a feedback system. So it can be able to kind of detect the vibration, calculate the vibration into it. So it can have a feedback system. So it knows that that's the vibration that's happening from the plane and it has to cancel it out.
Look at some papers because vibrations can be this type or shear
Yeah.
vibration. Look what other people do, you know, how to control this issue. Now, coming to the second part on machine learning. Machine learning, everybody, we want to apply machine learning, but becomes a little bit problematic. We have to define the landscape and see if it's applicable or not. For instance, my understanding is that you want to apply for real-time application, correct? Real-time. Real-time machine learning will be a problem because if you're planning to mount a system on the drone, the electronics, this is one of the problem in drones because they have limited payload and power requirements. Machine learning can be problematic. One way that you can do to bypass this, to be more realistic, people that are using machine learning in drones, if you go from one place to another, first of all, my understanding is your drone is semi-autonomous. It's not completely autonomous because you have access from the ground, correct?
It's semi. It's we can always take control at all times, but we want to make sure it's that a user that can't use the drone, that doesn't understand how to pilot it, like a normal pilot, we want them to be able to use it as well. So we can take over control, but it's mostly autonomous when it's in the air.
Okay, it's autonomous, but still, if it's autonomous, this is my point. To apply machine learning is a Herculean task. It's very difficult. People, what they do, considering the drone autonomy, because drone has autonomy, it has payload, it has power requirements, you can use templates. You can use templates pre-train machine learning. You provide the data to the drone yourself, okay, using templates. This is what people do if you want to include machine learning and bypass other real-time problems. Okay, so think carefully on this. My advice is to go and read a little bit on drones. You know, it's not a problem, and see the optimal solution. Okay.
Thank you.
For the feedback. Thank you.
Welcome. Very good study. Very good.
Thank you, Dr. Yakos.